In this lab 2, we'll be discussing about hierarchical modeling. Um, we'll get introduced to the Verilog, uh, and also we'll see the specific example as being presented into the simulation environment and see how do we do write Verilog code in that model sim environment. Also, how do we simulate our design in the model sim environment and look at the result of the simulation. Now, to start with, let's define an entity, hardware entity called D flip-flop. Don't worry about if you don't know already what is a D flip-flop or what is an inverter gate, combinational circuit, sequential circuit. It is basically very irrelevant right now for this specific topic of hierarchical modeling. Uh, the important part is that to see, okay, I have an entity D flip flop which has input of D, clock, reset, and output of Q from that entity. So essentially it means with certain logic values on the input D, clock, and reset, Q, we can expect certain output from this entity at the Q. Okay, and the behavior is kind of defined within this timing diagram, of where clock is a train of pulses in that signal port. Uh, this bubble, by the way, is called a negative edge triggered, denotes the negative edge triggered flip flop, which means any output changes only at the negative edge of the clock, which means when clock transition from logic 1 to logic 0. So let's say this is my clock train goes into this D flip flop, and my reset signal at some point of time it goes high and then it comes down and stays low. So this is my reset state when we are resetting the circuit. This is my output. This is my signal train at the input D. Now let's see what is the relation between clock, reset, D, and Q. So if you notice that Q remains at low as long as we are actually having the reset signal high till the very immediate transition edge, which is like falling edge for this specific flop, it remains 0. Right? Anything change happens to the Q only if resets is at 0 stage. If it has 1, it will just stay at 0 no matter what. Okay. Then what we see is that at the negative clock edge, the D at that point was 1, so logic 1, so Q transition to logic 1. Okay, and the next transition at the falling edge of the clock, Q remains 1 because D at that point D is 1. So it didn't reflect the event on the D when D became low for a certain time and become high within these two edges, falling edges. Okay, it happened, but it was at logic 1, it fell down to logic 0 and then recovered itself to the logic 1. So with respect to the Q at this falling edge of clock, the D value didn't at all change, so Q didn't change. Okay, so this guy had no effect. Next, if you see the next clock edge, falling edge, D is low, so Q reflected that and become low. Okay, so this is like kind of the output changes only at the certain clock edge. In this case, it is a falling clock edge. We know that from this schematic symbol with a bubble at the clock port. We know this is a falling edge or negative edge triggered flop. And this type of circuit is called a sequential circuit, which basically tells that only at certain edge of the clock the output will be changed. Okay, if any input changes in between, it doesn't matter. Okay. Now, on the other hand, there is the other type of logic gates is called a combinational logic gate or combinatorial logic gate, which practically reflects the change in the input immediately on the change in the output. For example, this is the inverter entity. We are defining that, and behavior is that this output is an inverted logic or negate logic of the input. So if input is 1, output is 0. If input is 0, output is 1. And those combinations. Now, if we look at the D trend, let's say the same D we are feeding into the flop, we are also feeding into the inverter. Then what happens to the output of the inverter? When D is 1, output is 0. When D is 0, output is 1. So it is the irrespective of the clock, it doesn't matter, right? It is not depending on anything like reset, clock or anything. It basically, whenever the input changes to it, it's basically the output is being reflected with the change of that input. So this is an combinatorial circuit, and we define that entity as an inverter because it's basically negating the logic at the input gate. Now, let's say we want to define another hardware entity called T flip-flop, which always toggles its logic at the output as long as the reset remains low. Like previously, this is also a flip-flop and sequential circuit. As long as the reset remains high, Q output remains 0. When it becomes low, then each negative transition of the clock at that edge, the output toggles. So it was 0 at this edge, it immediately toggles to 1. At this edge it was 1, now immediately toggles to 0, and it goes on like that. Okay, it just as long as the reset signal remains low, Q just keep on toggling with the clock changes. Okay, now to implement that, what we do, we take a D flip-flop, we call it a D flip-flop instance. Okay, so this is the top level port clock. So this clock goes into directly to the clock of the D flip-flop. Reset goes directly to the reset of the D flip-flop. So we instantiate a D flip-flop there inside, and now what we're doing, the Q, output Q of the D flip-flop is going out as a Q of the T flip-flop. So we are taking the output directly as output of the T flip-flop. And also inside this T flip-flop, what we are doing is instantiating one inverter, connecting the Q to the inverter input, and the output of the inverter is fed into the D. So essentially what is happening, after the reset, Q is 0, right? Then the input to the D is 1, like it inverted the logic 1. So next clock edge, Q will assume the D value, so Q become 1, which means fed into the inverter, negative logic 0, so D is now 0. Now next clock edge, Q will assume that value, so Q will coming back from 1 to 0, next clock edge. And as soon as it is 0, it negates the logic here, so it becomes 1, D is fed with the 1, very next clock cycle, clock edge, it will again assume that value into the Q, and thus Q keep on toggling till the reset remains at low. Okay, so that's a T flip-flop. So what we essentially did is we used two of the logic gates, connected them in certain fashion so that it actually implements the functionality of a T flip-flop. Now, using four of the T flip-flop, we define a ripple carry counter. So what is the top level schematic of that? I have a ripple 4-bit ripple counter, which output is kind of 4-bit is a 4-bit output, and that means it can count from 0 to 15, the 16 number in the binary system. So as long as reset is high, Q remains 0. Okay, the 0 0 0 0, like 4 zeros, right? And then as soon as the reset goes low, then it starts counting 0 1 2 3 4 5 till 15, and then come back to 0. Like after 15 it becomes 0. Like each clock edges, each clock cycles, the output changes from 0 to 1, 1 to 2, 2 to 3 till 15, and from 15 to 0, and again it cycles goes on as long as reset signal remains 0. So how do we do it? What we did, we instantiate like 4 of our T flip-flop, which we implemented in the previous slide, connecting D flip-flop and inverter. We instantiate them, fed the top level clock to the very fast clock of the T flip-flop, and take out that Q value or output value from that first T flip-flop as the Q0. Okay, and also that Q acts as a clock to the next T flip-flop. Okay, so we connect that, and output of the next stage T flip-flop is taken out as a Q1 bit, Q0 Q1 of this 4-bit mass, and also it fed into the next stage T flip-flop's clock. And in this fashion we just connect them, and reset is connected to all the T flip-flops, so that if it goes high, all of them immediately become 0 0 0 0. So that is the reset operation. Now, so that means essentially what we did, we have implemented one 4-bit ripple counter. Now if we actually zoomed into or dive into that circuit, what we'll found 4 instantiation of the T flip-flop. Now if we dive into one of the T flip-flop, or actually all of the T flip-flop, then we'll find that each of them contains one inverter and one D flip-flop, right? Now question is, can we dive down into the D flip-flop? Possibly no. That is our very basic get implementation. Okay, we'll see how do we implement that in the next segment of this video. But assume that this is somehow implemented. We have this is a basic leaf level logic cell, and we connected them and put them together as a T flip-flop. Then take the T flip-flop, put them together as a ripple counter. So essentially, ripple counter contains 4 T flip-flop. Each of them contains one D flip-flop and one inverter. So the ripple counter implementation contains 4 inverter at the leaf level. It contains 4 inverter and 4 D flip-flop, and connected in certain fashion. So we can see that it is an hierarchical approach to kind of implement and reuse the common things. So what is the common things? Common things like D flip-flop and inverter, we combine them into one T flip-flop entity, and we instantiate those entity into and connect them together to make a ripple counter. Okay. From object-oriented perspective, if you want to think, each of this entity is a class. Okay, so this D flip-flop is a class, inverter is a class, and instantiation of them is the instantiation of that class. Like, let's say there is a class A, and you declare a variable of type A as var underscore A. So that var underscore A is kind of an instantiation equivalent in the object-oriented programming, either in Java or C++. So essentially, this is pretty much, like, in the conceptually, it is pretty much similar to what you usually do in the programming and software programming, object-oriented programming using Java and C++. So each of these, we have a top level definition of the cell, which is kind of act as a class, and then we instantiate it, kind of a declaration of a variable in a top level implementation. We'll see the implementation. So how do we write it in terms of Verilog language? The class, the object oriented programming, if you know, there is a class declaration like that. We have in the Verilog called a module. Okay, so within the module, we define what the behavior of that specific module. Okay, so we define a D flip-flop, and then what we define, okay, list of ports. If you remember from the previous slide, we defined this entity. We have 4 ports: D, clock, reset, and Q. Right? So we define that list of ports, and then we clarify that D, clock, and reset, these 3 are input ports, so signals are coming in, and Q is an output port, so it is an output from that specific module. And then we have some implementation. We'll see in the lab example code section, but just some implementation is there. And then we end the module definition as with a keyword end module. So any entity is defined within a module and module block. Okay, and then we give a module name, like D flip-flop in this example, port list, and then we clarify which port is what type, in some implementation code, and then we end this definition or entity definition as with the end module. Similar for the inverter module, we name it inverter. Port list is just one input, one output port, out and in. Then we clarify which port is what type. Some implementation, we'll see later, and then end module. So we define that entity. Now, if you recall, T flip-flop is instantiating one inverter, one D flip-flop. Okay, and it has like 2 input port, clock reset, 1 output port, Q. How do we do it? We define a module again, T flip-flop, entity definition, list of ports, Q, clock, reset. We clarify which type of port they are. So clock and reset is input port, output is Q, and there is something called intermediate where, internal connection, or where it is called D in. We name it just a D in. Where is the keyword? D in is just a name, like a variable name, you can say. So conceptually what it is doing, if something is not a port, so for example, clock is a port, we can connect them. Reset is a port at the top level, we can connect them. Q is a port, we can connect them. But this Q also we can connect to the inverter port, input port. But if you see this output of the inverter and input of the D flip-flop, it's an internal connection. So how do we define it? We define it as a where. So just think of, like, if you have electrical component, you are just connecting with the real wire. It is just the same concept. We are taking like wiring the output of the inverter to the input of the D flip-flop. Okay, so that is the where statement here. Now we're instantiating. Okay, so we say, okay, what is my entity type, like D flip-flop, then instance name. It can be anything. We just use dff underscore inst. Then we do some connection port list. So what we do is that we say dot q means port q connection to the queue of this port. So this queue belongs T flip-flop top level port. Okay, so we are connecting this top level queue port to the queue port, like dot q. By the dot q means queue port of the D flip-flop. Okay. Similarly, dot clock means of the DFF CLK port of the DFF we are connecting to the port of the T flip-flop. And reset, similarly, the reset port of the D flip-flop is being connected to the reset port of the T flip-flop. Now, for the D port, if we recall the circuit, logic circuit here, see the D port is connected with the internal wire from the output of the inverter. So, what we connected the D port of the D flip-flop, D port dot D with the D in, the internal wire. Okay. Now, as of the inverter, as far as the inverter is concerned, again we name the entity type like inverter, instance name, anything can be that. We just choose it to be invert inv underscore inst, and then the output port is connected to the D in. Right, that's where the connection is made. So output port of the inverter connected to the input port of the D, and we are connecting them internally through a wire. So we are doing that. See, D in here connected to the D flip-flops, the instance of the D flip-flop to the port D, and also the same wire is connected to the output of the inverter instantiation, output port of the inverter instantiation. So to complete that connection, so D port connected to the output through this wire D in. Conceptually, when we say like I connected this port to this port, is conceptually it's kind of a wire, but since they are the port, like top level port, we don't need to explicitly declare them as the wire. Okay, they're like all the ports are implicitly an wire. Okay, so when we say that I'm connecting the Q port of the D flip-flop instance with the Q port of the T flip-flop, implicitly we are meaning there is an wire connecting from the D flip-flop internal port to the external output port of the T flip-flop, like the top level at the top level hierarchy. Right. So this is the connection how we do. And once we have this entity defined, what we do, we define a ripple counter module, the entity ripple counter, which we recall the port is clock reset Q, but Q is in this case is a 4-bit. So we kind of see how do we define. We still define Q clock reset. Input is clock reset. Output is Q, but we have a special notation here. See, within the square braces we have 3:0, which means this guy is a multi-bit bus or multi-bit signal, which has like 4-bit of width, 0 to 3, indexed from 0 to 3. So 0, 1, 2, 3. So we can actually go and tell them, we can actually refer to the individual bit as a Q of that index number. Okay. Now what did we do? We just reflected whatever we discussed in this connection. First level, the top level clock goes to the first level T flip-flop of the Q0, and then that Q0 goes as a clock of the next stage, so on and so forth. So we'll see that. So if we look at the reset, dot reset of the T flip-flop port is connected with the reset of the ripple counter. So if you can imagine or want to imagine in this way, like see my top level port connected to the T flip-flop port through port of reset through a wire, and that reset port is connected to the D flip-flop reset port and with an wire, and it goes in there. So if you see from the top level reset, it's actually traversing through the hierarchy. It goes from the top level to the next level of T flip-flop. Inside the T flip-flop, reset goes into the D flip-flop. That signal goes inside and do something. We'll see what it does in later section. But the concept is you need to be very clear on that concept. That is whole hierarchical modeling in a digital design. So top level things goes down through the hierarchy, and we use the hierarchical modeling and instantiation to kind of reuse the implementation code within a digital design domain. It is the same philosophy as object-oriented programming. The main philosophy of object-oriented programming is to minimize and reuse existing implementation. Same with here. Okay. Anyway, let's come back to the connection. So first level, TFF0. So this is instance name. This is the entity type. So which is T flip-flop. So 0, 1, 2, 3. This 4 entity. The port, output port of this T flip-flop are connected to Q0, Q1, Q2, Q3. Just read this smaller q as a capital Q. This is a typo. Please note that these are all capital Q, the big Q, not the small q. Otherwise you might be confused. Okay, so my Q port of the T flip-flop is connected to the Q0 output port, that first bit of the output port of the outer ripple counter. Now the clock is kind of a stage by stage or progressively one stage output goes as a clock as the next stage. So how it goes, the top level clock is connected to the first level clock port of the T flip-flop. Then the next level clock, T flip-flop 1 clock, is the Q0. So whatever output of the first stage T flip-flop goes as a clock in the next stage. Whatever output of the next stage or second stage T flip-flop goes into the third stage clock, and so on and so forth. Okay, so that's how we define an instantiation based hierarchical modeling. Okay, so once we do that ripple counter, then of course the obvious question is that how do we test it? Okay, so that means we define just an entity, that how does it look like. Okay, we must instantiate it within a top level block, like we call it a test environment, test structure, and there must be another block which is probably driving the clock and driving the reset signal with certain patterns, and the output from the ripple counter must be taken into some observation. Like we need to observe that whether it is doing its function correctly or not. It can be a visual confirmation, it can be an automated test, but whatever it is, the output has to be consumed by some part in the Verilog implementation for testing. Okay, and this is very important stage. The test bench, so when we implement it, then we want to test it. So top level module is get instantiated, and that module being driven by some stimulus generated from the test bench, and the output is being taken into the validation part of the test bench program to kind of validate. Either can be visual validation, can be automated validation, programmatic validation, anything, but it has to be observed, those output, and make a decision, okay, this is whether a block or entity is functionally correct or not. So we'll see in the next segment, we'll bring up the simulator model sim and do the experiment as we described here. We'll implement this ripple counter and observe it output. Now to perform the lab 2, what we all need to do is go to our Canvas home page and our course home page, and there is, you can download the lab 2 experiment code. So there is no preview, so we download it. Okay, started downloading, it's done. Let's say go to the download lab 2 and compress it, extract all. Okay, I want to do it here, so I got an directory which has the different definition like D flip-flop definition, inverter definition, R counter, test bench of the ripple counter, and a T flip-flop definition. Now to simulate, what we need to do is to invoke model sim. Okay, hopefully by this time you all have installed the model sim, and then we do what we do is basically file, new, project. Just give some project name. Let's give CS147 lab 02. Okay, and project location, by default it goes into some location within the installation. I would always prefer to actually go and put your own installation sorry, point to your own directory, not the installation directory. That would be like maybe here, downloads lab 2. Okay, so that's where we downloaded our source code and temporarily extracted that code. You can use some other areas too, but I would suggest not to use the installation area to do your work. The other options you can put it as a default. Okay, then it gives you certain options to create new files, simulation, etc., etc. We just want to add some existing file because we already have them. So we have all the files, so you can select all of them by pressing the shift and down arrow key. Open. Take the all the default option there, and okay, close. So what you see in that project pane, we just have imported those 5 source files, and we can actually go and look at the source file. Of course, like for example, let's look at the inverter. So we double click on the inverter and see that we have the inverter module, and these are the comments. Okay, but entity name is a module, end module. Okay, port list out in, input is in, output is out, and then the implementation is that assign out equals, this is the inversion sign, little tilde, inversion of n. So what it is meaning is that it is actually define a relation between input port and output port, so an inversion operation. So assign out as inversion or negation of the input port. So that's very simple inverter stuff. And then let's look at the DFF. How do you do it? DFF, again, port list, input is D clock reset, output is Q. Now since this is a sequential element, we need to drive the output with a logic, some logic, which is usually case the register type of variables. Okay, so output is Q, and also we define something same name variable as Q as a register type, which can register is not a hardware register that we actually study later in the semester, but this is like a more like a storage inside the simulator. It says, okay, store the value of the Q, and then you can drive it through the port. All right. So we define a range. Now it says always, these are all the keyword, the red things are all the keyword, always at positive edge of the reset, that means reset goes from logic 0 to logic 1, or negative edge of the clock, that is clock goes from logic high or logic 1 to logic 0. So if any of that event happens during your simulation, positive edge of reset or negative edge of clock, then evaluate the block within this begin and end. Okay, so this is a block of code to be executed. You can think of this as like curly braces in Java or C or C++, like open curly brace, close curly brace replaced as a begin and end. Now within the block, what is saying is that if reset means reset is high, is true, then Q equals 1 bit 0. So this is saying this is binary format number 1 bit width with a logic value of 0. Okay, so if reset is high, we put 0 as a Q, and that Q being stored in the simulation register and being driven to the output port of the D flip-flop. Else, just make Q equals D. So whatever is coming in as a D, transfer that logic value into the Q. Okay, so that's what the whole operation of D flip-flop is, as we described in the slide, that if on the negative edge of the clock, if reset is not high or if reset is low, then transfer the logic value at the input port D to the output port Q. So that's all we are doing here, describing whatever we described in English, we described it as a Verilog. So always at this two event, either of them happened, go and evaluate this block, and if the reset is high, assign the output value as 0, which is stored to be stored as a range variable. Else transfer the logic value in the input port D to the output port register. Okay, so that's D flip-flop description. Now from that we did T flip-flop as we described in the slide, right? Port list, input and output clarification, some internal while Q inverter, then we instantiate T flip-flop and inverter instantiation, connect them, and we have the T flip-flop. Using the T flip-flop, we have ripple counter, same as what we did see in the slides. Now the test bench. This is little important, just pay some more attention to this. Very first line is called a time scale, which tells that my whatever time I define within the simulation is in the nanoscale unit. Okay, nanosecond unit. This is like a resolution of the simulation, but don't pay attention right now onto that 10 picosecond stuff. It's advanced thing. You don't need to know as of now, but this one you need to know. Like this is whatever time we are defining, it's a nanosecond scale. Now we defined a module ripple counter test bench. You can give any name there, but observe that this module doesn't have any port list. So it is very top level block from Verilog perspective, that it doesn't have anything port. It's all the required things are coming from within inside of that module. But apart from that, it is the same module and module. Okay, then we define some storage is a test bench clock, test bench reset to drive the signal, and also test bench underscore Q, which is a 4-bit variable or 4-bit bus to observe the output from the ripple counter. We instantiate the ripple counter, connect the ripple counter port Q, which is like 4-bit bus, to the 4-bit wire here, and also the register port. Clock port is driven by the register TB clock, and reset port is driven by the register TB reset TB. So that means whatever value I put there in the register, that logic value will go inside the ripple counter module to be evaluated in the simulation cycles. And now after that we have something called initial. Initial means anywhere you see an initial simulation perspective at the time 0, very beginning, whatever follows that initial will be executed. Whatever follows that initial. In this case, we stuck a begin and end block, a block of code with the initial. So that means at the simulation time 0, all this statement will be executed. Okay, one by one. Okay. So what it does, it sets the TB clock value, register value to 0, reset to 1, that means it's in the reset condition. So it is kind of driving that logic through the ripple counter through this port dot reset and dot clock. Now this one hash 15 means after 15 nanosecond from the last event, which is at event like 0 time event. So 15 nanosecond, make the TB reset down. Okay, TB reset down, and from that point, after 80 nanosecond, why nanosecond? I told you that there is a time scale. This one, 1 nanosecond scale. So any number, time number we define is in the nanosecond. So after nanosecond, that means after this point, after 80 nanosecond, you again raise the reset signal, hold it for 20 nanoseconds. So after 20 nanosecond, bring it down, and after 320 nanosecond, it bring it back, and after that 50 nanosecond, we do something called $stop. $stop is a very Verilog directive which direct the simulator to stop at that point. Okay, so halt, and after that it ends. Okay, so this is the description of the initial block, and we can see this TB reset signal goes and up and down within the specified time value in the simulation deck. The other block we discuss here and implemented here is always block. Always means like it's kind of while one statement in the C++ or C and Java context. While one, like that code after this always keyword will be executed forever till it comes to a stop or halt the simulator. Okay, so always is like always, like while one, while true. Now within that we stuck again a begin end block, though we didn't need it because it just has a one single statement in it, but it's a good practice to always start a begin end after always an initial block, initial keyword. So it says after 5 nanosecond, make the TB clock logic inversion of TB clock. Okay, so TB clock was 0. That means after 5 nanosecond, make it 1. From that, after another 5 nanosecond, make it 0. From another 5 nanosecond, it make it 1. So it keeps on toggling. And for how long? Forever. Always. This always, forever, till the simulation come to a stop. Okay, so these are the sequence of event we can observe in the simulator. We'll see how to do that. So once you download this source code, created the project, and let's say you studied this code and so on and so forth, maybe you can want to try some modification of the code as well. There is some compilation switches. Important is that this one is compiled, so whatever file is being selected will be compiled. Okay, this one is compile out of date, means whichever has a status of query is out of date, means it has been, probably it has not been compiled or has been compiled, but since then the source code had been edited. So this is the one. and this is compile all, so it doesn't matter whether you have edited, re-edited or not, it will compile everything together. I usually use this one because our project is very small. It doesn't actually take much time to compile them, but for other bigger project it might be a problem. People want to do like this one by one, just to see, change one source code, just quickly want to compile that and see if it is going through or not, or compile all the out of date files and don't touch whatever not edited. It's just a choice. Anyway, we hit that button, and then all these source code are kind of compiled, and then what we do is go to the library tab. So here is a project tab, library tab. There is a library called work, and we find out something of TB. This is our test bench module. So remember, only the test bench you can simulate. You cannot simulate these, that, or TFF, nothing. Only the TFF. Okay. If you can double click on that, but it will not do anything. It will just load and sit there. There is nothing, no simulation instruction there implemented within these other modules. So anyway, we double click this part. See if everything is okay. You probably will get this kind of layout. Layout simulate. You can change the layout to something else, but by default it goes and do a simulate layout. Anyway, I'm resizing the windows. So what I want to do here now, I select, these are the top level signal names or register names and where names in the within that module. So I can go and select. So how I'm doing, just go and click on that one, and then using the shift, pressing the shift key, I'm just using the down arrow to select them all. You can do a mouse selection also by holding the left button and just play with the GUI. There is nothing magical about it. It is all intuitive. So once we do that, right click, add wave. Okay, so it will bring out some wave things. Okay, it brought out outside the window. Let's say you want to just push it in the main IDE. Okay, so it becomes like a source code, one of the source code tab, like we have a wave. There's nothing in the wave so far because we haven't simulated anything. Now to simulate, we have like a couple of buttons here. So this means run, but run till for 100 picoseconds. We don't want that right now. This one is continue to run. Let's say there is a halt or stop. This is kind of debugging through the code. You don't need it for this lab, maybe later. This one is run all. Run all means run till you hit a stop statement, $stop statement. Okay, so we hit it. Okay, see, it executed, it simulate, it come to that end, $stop at this point. Now what happened to the wave? We have something here, we don't know what. So what we need to do is zoom out a little bit. Okay, oh, there is too much. But see, some signals are kind of fluctuating, toggling, like there is some activities going on there, right? So let's zoom a little more. Okay, so here, let's do, before we dive into the this, I would say let me explain this button. This button is that, let's say you recompile, you edited some object, recompile this, recompile your project. Then to simulate again, what you need to do is, this is a reset button or restart button. So you can restart. Okay, so waveform are all gone, and then do another simulation. Okay, if you don't do it, simulation will start from this point. Let's say from this point, and after this point it will just, there is nothing stop, no activity, just keep on going. You won't see anything. It will probably hang your system. So be aware of that. And if you do want to rerun, make sure you hit this rerun restart button, so it will reset everything from the simulation perspective, then do a run all. Now let's see what it does. This is my clock signal. This is my clock signal. See, it is toggling every 5 nanosecond. Every 5 nanosecond clock train is coming up. And okay, let me bring the reset to up. So I'm left click holding the mouse and just move it up. Okay. Now see, at 10-15 nanosecond, the reset signal went down as we defined here, right, to make it down. Then after that, after 80, that means we'll see at 95 nanosecond, TB reset will go up again. Let's see, 95. Here, this is 90. Yeah, this is 95. It goes up again, goes down as we told them. And let's see what is the output of the ripple counter. Now you can select these, and since we are more familiar with the decimal system, I changed the radix to unsigned. Okay, so it immediately changed this 4-bit number. You can expand that also by bit, and you can see how the bits are toggling. However, we are interested to see what is the absolute number coming out of that. So behavior is that when the reset signal was high, everything was 0. As soon as it become low at the negative edge, it become 1, 2, next negative edge 3, 4. It just go on 5. Let's say till what time? 8. And after 8, the reset signal goes high, so it makes the output 0. Then it becomes low here, so that means it's restarted the counting from 1. And let's see, 1, 2, 3, 4. It goes on simulating 15, and then after 15 it will become a 0. Again started counting from 0, 1, 2. It just goes on till at the end, some point of time, we made the reset signal high, so it resetted the output to 0 and stayed there till the end of the simulation. So this is how we load the source file, create the project, compile it, simulate it, observe the output in the waveform. Later also we'll see how can we do some print of certain logic statement within the test bench program, which will be very useful for debugging. So I'd suggest you guys all to try this lab, download the source code, create the project as a step by step as you have seen. Just try the simulation for yourself. You don't need to change any code or anything. It should work as it is. Good luck with your experiment.